what you need to do is go into this mesh morphing optimization. We're just going to download the archive file from there, put that in our downloads folder. So what we're going to do today is called it's the mesh morphing optimization. So we saw topology optimization, and that works well if you kind of have a blank slate design, trying to find an initial design point. What topology optimization is not good at is trying to modify an existing design. So if you have an existing design that's pretty close to what you want to do some changes of dimensions or kind of just short or small amounts of change from that existing design, topology optimization not necessarily great for that. So that's where we have shape optimization. That's what we're going to look at today. So once you have Ansys launched, what we're going to do, I think the easiest thing to do is just double click on the archive file. So that's what I'm going to do. So I'm going to go to my downloads folder, either right click on the start, go to File Explorer, or just click here and go to the Documents folder. Either way, I get to the downloads, and then this is that plate mesh morph activity that just downloaded. So I'm just going to double click that. That's the easiest way to open the archive file. First, what we're starting with is the topology optimization that we did last time. So that's kind of our starting point. So I'll just remind us what we did there, and then we'll continue on with this mesh morphing exercise. I'm just going to close the empty window here. It's going to give you a couple warnings when you open it. Just click OK through those. All right, so here is that schematic we had built up with the topology optimization. So I'll go through this as you're kind of loading things up. We started with this plate of material, and we did a topology optimization, and that gave us a shape. This one we did two different ones, where we did one where we did compliance, compliance minimization, which is maximizing stiffness, while setting a mass target. That was the first option we did. Second option we did was we set a stress target and minimized mass. And so I'll just look at, and then we did a verification run. So I'm just going to open this up. You don't need to open up this part, but I'm just going to show you what we ended up with there. If you recall, we had the geometry, we exported it to space claim, then we were able to extrude out a solid from that geometry. And then because once you get to the topology optimization results, you don't know how it's performing until you do this verification, kind of create a new solid to verify the performance. That's the one I'm opening up now. And actually, if you have it open, you can go ahead and double click on that setup on that last one, because we're eventually going to need to open that one anyway. So double click, once you have the Ansys open, double click setup on this static structural that's shown there. So I go to that geometry. This is one of the shapes we came up with during that topology optimization. So the issue we're trying to address with the mesh morphing and how Ansys kind of changed naming to shape optimization is, what if we want to kind of start from this design, just kind of modify this design to get a little bit better performance. And that's where topology optimization always forces you to start from the beginning again. And you get to this design point where you're not able to do much with it. The other thing topology optimization can't do is add material. Can't make the design larger in any way. So we're going to look at mesh morphing as a kind of way to do that. So let's once you have your schematic open, what we're going to do, and again that downloads under week 10, download the mesh morphing activity archive file, double click on it once you have Ansys launched. Once you have that open, what we're going to do is, it's the same block as topology optimization, it's just a different option in there. So we're going to drag this structural optimization. So what we're going to do is take this structural optimization, attach it to the solution of this last static structural block, the one we just had open. So static structural optimization, it's important to drop on the solution to that static structural. So if you have it correct, you'll have 4 connections, with the last connection being the solution to setup. If you got it wrong, just delete it by clicking that arrow and re-drop it onto solution. Again, we're using the structural optimization block, which was the same one we did for topology optimization before. So we'll double click setup on that structural optimization. Once we drop it on the solution of that last block, that's really just the same window we had open. if you hadn't opened it before, it'll take a little bit for it to open up. So we get this additional structural optimization, which defaults to topology optimization. And so there's a few settings we need to change. Under analysis settings, we'll leave that the same. We do need to change the optimization region, because that not only allows us to select which parts we're going to optimize, but the type of optimization we're doing. So under that structural optimization, we'll click on optimization region. So before we looked at topology optimization, which is the default, we're going to switch it to shaped optimization. Okay, so that's what Ansys is calling this mesh morphing. So we drag it down to, again, optimization region, drag it down, type, switch from topology to shape. Okay. A similar one that it has is this topography optimization, which does a similar thing, but if you have like a shell mesh, it works for shells. For a solid mesh, we want to do shape. If your project did have a shell mesh, then topography might be the option to try. We're going to do shape. Now you notice one thing that happened is we've lost our selection. Before it had the whole body selected. Now that selection has switched to a question mark. And so what we need to do, the reason that is the case is the shape optimization, what it's going to do actually is move the nodes around in our mesh to optimize it, to change the geometry. But it only works on a tetrahedral mesh. It doesn't tell us that, but that's why it's yellow here. So we actually need to change the mesh type to a tetrahedral in order to select the solid, because right now I can't select. I can select it, but it's not going to let me apply it. So what we need to do is scroll to the top, right-click our mesh, and what we're going to do is insert a method. A method is a way for us to specify which type of meshing Ansys uses. By default, it does a quadrilateral dominant mesh. That does have some efficiency benefits in terms of accuracy and for a fewer number of nodes, so that's a speed up. But for this morphing, we have to do a tetrahedral mesh. So what we're going to do is click on our mesh on the tree on the left, do insert method. We just need to change, well, we need to select the whole geometry. So we'll select that, just the whole solid. Click on the geometry and click apply. So you have to select everything and do apply, just the whole body. Then we switch from method from automatic to tetrahedrons. Okay, so that gives us a tetrahedron mesh, so basically the triangular mesh instead of the quadrilateral mesh. Now we do have to remesh it in order for that selection of all the work in our optimization. So we right-click just the mesh. We don't need to rerun everything right now. Just right-click the mesh and do generate mesh. That'll remesh it as a tetrahedron mesh. We'll know that it worked, but we'll see a bunch of triangular meshes on the surface. You can see that. So it's just, this is a requirement of the shape optimization. It only works with tetrahedron meshes. Part of that is when you start moving these nodes around, it affects mesh quality, and the triangle mesh is a little more robust to that moving around of nodes. So we're going to go to, now we can go to optimization region. You notice it's checked now. It automatically pulled in that triangular mesh for us. So then I've tried a bunch of different options here. I'm going to give you the set of options that kind of work best on this model. You may need to, if you use this technique on your projects, you may need to try some different options. What we're going to do here is what I found works best on this particular model. What you'll find with shape optimization, there's a lot of ways to get kind of crazy looking results, or results that fail. It says it doesn't converge. So you just kind of have to play around with it, figure out what's going to work for your model if you choose to use this approach for your projects. What I'm going to do is the objective. Right now it has compliance minimization and a constraint of a mass target, which is a default it has for topology optimization. That setup doesn't really work really great on this model. What approach we're going to take is try to maintain the current stiffness, okay, while minimizing the mass. Okay, that's the approach we're going to take. So we need to change the objective from compliance. So under structural optimization, click on objective, change from compliance to mass. It's already at minimize. So we're going to target minimizing mass. But to do that, we need to put some constraint on it. Right now, I'll just push all the nodes together to get 0 volume. So we need to change the constraint. It doesn't allow us, this response constraint, it doesn't allow us to change it while it's there. We have to delete it and add a new one. That's one of the changes that's requiring me to re-record this video. So what we're going to do is right-click response constraint and just delete it. Okay, and what we're going to do is a compliance constraint. So we've changed objective mass to minimize, and then we right-clicked that response constraint and deleted it right below the objective. Now we need to get to the context menu like usual here. We're clicked on objective. We need to go to context menu to see the right options. One of the options is response constraints. We need to add a new one. We just deleted the one that was there, which was a mass target. Instead, we're going to minimize mass, but what we need to have something that kind of balances that so it just doesn't push the mass to 0. So we're going to do a compliance constraint. So what we want to do is our target's going to be minimize mass while maintaining this current stiffness. Okay, so drive mass down while maintaining stiffness. So we're going to use that as a compliance constraint to do that. So with the response constraint, you see it's yellowed out. It's asking for a value. It's asking for a value in joules, which seems kind of strange. But what it's really asking for is the strain energy target for the deformation. And so strain energy, just how much energy is stored when it's displaced. And the greater that is, the more kind of deformation you have in the model. And so we want to kind of maintain the current deformation energy for this compliance constraint. So in order to do that, we need to determine what the current, this number, we're not really tracking it normally. So we need to figure out what this number is for our model. Okay. So up here, we do have the current static structural set up. We need to, so if you scroll up on that feature tree, what we need to do is go to our solution. We need to add a compliance solution. So that static structural, what we're going to do is make sure we're in the context menu. We're under static structural solution. We're going to click result, and we are going to go to strain, or actually, sorry, energy. Click that and do strain energy. Okay, so that's going to give us the initial compliance of the model so that we know what the target to keep it constant. So we're going to do strain energy. So that gives us the strain energy of the model. So what we're going to do is right-click that and then solve. So we remeshed it, so we need to resolve it. So again, under static structural, under solution, context menu, we added, just like a stress plot, we had a result plot of energy, strain energy. Okay? We're going to right-click that strain energy and hit solve because we remeshed it, so we need to resolve that model. Should solve fairly quickly with this kind of coarse mesh that we're starting out with. Like the one thing you'll find, like the topology optimization, where it was pretty sensitive to mesh size, we saw that. This morphing is also pretty sensitive to mesh size. Obviously, the more nodes you have, the more freedom it has to try to modify the geometry. But also, you have the trade-off that it's going to take more time. So what we want to look at, we don't care so much about the plot. We care about the total strain energy because that's what our target's going to be. So if you click on the strain energy plot after you've right-clicked and hit solve, and if you don't have this part done, it's okay because we just need the number. I just want to try to do it. We need the number. It's 2.59 times 10 to the minus 2 joules. Okay, so that's the number we need for that compliance target to maintain a current compliance. So we just needed this to figure out what that target should be. So here we go to the response constraint, which still has the question mark by it. Under compliance, we now know that it should be we'll say 2.6 times 10 to the minus 2 joules. So 2.6 E minus 2. 2.6 times 10 to the minus 2 joules, which matches the total, what's important is the total of our previous model. So even if you don't have the strain energy, under response constraint, enter that value. 2.6 E minus 2 for the compliance. So that's going to set the minimum. Okay, so now we're minimizing mass. We want to keep the current stiffness. That's what that will do. We're going to add a couple plots to our initial static structural because we need those when we do the verification run after we do the mesh morph. So under solution on the static structural, I'm going to add just a normal total deformation plot, and we'll add a von Mises stress plot. So equivalent von Mises stress plot and a total deformation. I'll just right-click both of those and retrieve this result. This will just be a point of comparison. We see what the initial displacement is. The other thing is I have it in meters right now. I know the topology optimization, it really needs to be in meters to work correctly. For the mesh morphing, I'm not as sure. The safest thing may be to go to Tools, and probably won't have you switch it now, but I have it in meters. If you're using your own computer, it's the only reason it would be in different units. It might be in millimeters if you're on your own computer. If it's in millimeters, just leave it for now. If you did change it, you have to right click here and say clear generated data, otherwise things aren't going to run. So just leave it whatever units you have right now. But just if things behave differently than what you're seeing up here, you might be because they're in millimeters. It shouldn't matter, but we saw in topology optimization that it did matter. So we have the total deformation, total stress. We're just going to use that to compare our new results to. The other thing I want to show you is in the optimization region, there's a couple parameters here. Turns out the defaults are okay for this model, but you do have the move limit per iteration and total move limit on the lower left here. These allow you to specify, you can enter a number there. We'll leave it as program controlled. You switch it to manual, you can enter a number, and that just tells you if it's morphing kind of too much per iteration, as we'll see. Those are numbers you can adjust to kind of fine tune it. For this one, the program controlled works, but if on your projects, if you want a little more control over how much it's able to morph per iteration, which is about 1/10 of the number of total, you can adjust those there manually. So what we're going to do is we're going to go to solution. We're going to hit solve, and then I'll kind of walk around as it's going. But let me show you how to watch it as it's going here. Let's allow access to all this. We can click OK on that. So what we're going to do is, under the solution information, we're going to click on this topology density tracker. What that allows us to do is see it as it's morphing it. So each iteration. Initially, it'll get kind of weird shaped, and it'll kind of eventually converge in on the shape. But if on your projects, if this gets too wacky at first, it's moving too much, you can adjust those move per iteration and total move. All right, so it looks like it's, at least mine is finished here. So what I want you to do, just to get credit for participating in this activity, take your screenshot now, whatever you got, even if it's not running, just of whatever Ansys window you have open. Just take a screenshot of that, submit that to get credit for this assignment. So we got this shape out of it. And so you can see why it's called kind of a mesh morphing approach to optimization. It's taking your initial mesh and it's just exactly what it's doing, morphing it to get a new shape. And again, to have more control over how much it can morph, that's where you go to the objective region. And when you switch to the shape optimization, you get these move limit per iteration and total move that you can kind of set. Those are distances. You can set how much it's moving. All right, so we go to the topology density. And so again, just take your screenshot, save it, and that's what you're going to upload at some point to Canvas. What we're going to do now is go back to the schematic window. Okay. Now we're going to do the verification. So we're going to, right now, all we have is the new shape, right? We don't know how it's behaving. We don't know how it's how much displacement, how much stress it's going to have. So we need to do a verification run in order to do that. So we go to our schematic window. We've done this before, so we're going to take the results and generate geometry and work on that. So we're going to right-click results. There's two options here. There's transfer design, validation system, geometry, and model. What's going to work the best is geometry. What that does is it should work with space claim, but space claim, as we had seen last time, gives us some errors when we try to open in space claim. So we're going to actually use discovery, which is basically Ansys' new version of space claim. Seems to not have that error that we got with space claim, some people got. But it's important that we do the geometry option here. So again, we're back on our schematic, right-click the results of that structural optimization, transfer design, validation system, geometry. Now, if you don't have the results here, It's really the same thing if you'd right-click it on this original structural optimization, so you can still kind of walk through it and do the same thing there. If you don't have this new one working or done or whatever, you can go to this results here and right-click it. Also you'll be replicating this block, transfer to geometry. So right-click results, transfer to design validation system geometry. So click that. That'll take a little bit to update. We may see the workbench window pop up. So what this is going to do is generate a solid, take our mesh from our mechanical window. It's going to make what's called a faceted solid in space claim or discovery is what we'll be using. And then we need, in order for that to work back in Ansys, we need to convert that to a proper solid that Ansys understands. So right now it's generating, okay, looks like it went through. So when that happens, you'll get this new static structural block. That'll be our verification run, kind of analogous to this previous one we had here. So what we're going to do is right-click on that geometry there, and we're just going to do update. So even though it's created that block, it still needs this update step to tie it in. So what we did was right-click results, design validation system geometry. And then once that static structural popped up, we just right-click geometry and said update. That takes a little bit. I'm not sure what the distinction between those two steps are. Seems like it should just be one step. But so last time what we did in Space Claim was we kind of took out the 2D geometry and extruded it. That worked well because it was a uniform thickness part. As we'll see, it did modify the thickness in some parts of the structure. That strategy won't work. So what we're going to do is, I'll show you how we could do that, but what we're going to do this time is just convert that faceted geometry directly to a solid and work with that instead. The other thing that as we'll see, that Space Claim will allow us to do is to, a couple things. It's going to have the original geometry and the new geometry. That wasn't as useful in topology optimization because it was just a plate, right? But now we actually have that shape. It's going to show us the new shape overlaid. So we're actually going to see the modifications kind of overlaid like that. Looks like it finished now because I got that green check. So now once that icon changed as well. So once that happens, and I'm just going to double click on geometry. So just double click geometry. In the past we right clicked and went to Space Claim. That's generating an error. So we're just going to double click. That's going to, oh, now it's doing Space Claim. I thought it would. It doesn't matter as long as it opens. I thought I was going to do discovery, but it was different on my computer. Hopefully, I won't get the error message. I think whatever it defaults to, you don't get the error. So I'm hoping that works. Because some of you may get discovery if you're on your own computer, and the steps are basically the same on discovery. So this is what we get, and this is what I mean, where we see the two designs overlaid, right? So now we can get a pretty good view of what changed. We can see that unlike a topology optimization, has actually increased the overall footprint of the design. Though you notice that where we had the constraints, both the fixed constraint on the left and the force constraint, it does treat those surfaces as fixed, so you can't move those. But everything else it's allowed to move, so you do have it's growing taller, which kind of makes sense. We're trying to keep stiffness the same while reducing mass. It's going to push away that neutral axis to try to make the structure overall stiffer. Little bit of modification in the thickness direction in some places, but it's mostly kind of in this XY plane. So this, and you may have a discovery window open if it was your own computer, so it depends on the setup, I guess. I'm not sure what changes that setting, but it does work the same. In discovery, you have this tree on the left as well. A couple things we can do. We don't even know how much mass reduction we got at this point, right? So that's one thing we can look at. So we can go to measure mass properties, and we just click on the solid. So that's our original solid, and it gives us the volume of 14,000 millimeters cubed. Okay, so that's our initial volume. I don't have a mass here because I don't have a material assigned. I probably could assign structural steel here, but I'm not going to worry about that. We'll just compare volumes. So we have 14,726 millimeters cubed. Now I can look at this body. This is what it's calling a faceted body. And it also gives me the volume of that. So we went from 14,000 to 11,000. So we have some reduction in the volume. And so what we want to do is see how much this impacted our stiffness, okay? And so what I want to do is I don't need this initial volume in my simulation. So what I'm going to do is right-click that solid, and I'm going to do suppress for physics. What that means is it's going to suppress that, so it's not even going to pull that into Ansys. And also I just want to hide it, so I'm going to uncheck the box next to it. So now we're dealing with just our faceted geometry. That warning that pops up just says hiding doesn't suppress from physics, which we already knew that. All right, so last time we did a sketch, and we sketched on a plane and we extruded it. This one we don't have kind of that convenient plane. You don't need to do this step, but I'm just going to show you how you would do that even on this geometry. So if I go into design and I go into sketch, before we tried to find a flat surface, but here we don't have it. But if I like click on the Z plane, I'll automatically get the normal plane to that. Now, right now it's only intersecting part of the model, and so I don't get that kind of clean geometry to extrude. But I can move that plane. So if I click the move, and that move triad comes up, and I drag the axis, I can find a spot where I get a good cross section, and I could extrude that. So that is still an option if you kind of wanted that uniform thickness shape extruded. We're not going to do that for this one, but just kind of showing how you could do that. So I'm just going to escape out of those tools, go back to design 3D view here. I can just take this model directly and convert it into a solid. That's what I'm going to do. So this body on the left, I'm going to right click on it. I'm going to convert to solids, and I'm going to click the merge faces option. What that merge faces does is if there's triangles on a plane, it'll just merge those into one surface. The do not merge faces will keep all the triangles in the model. We want to minimize that, so we're going to just do merge faces here. What that's going to do, so I just right clicked on body, convert to solid, merge faces. That converts it into a solid. Okay, so that allows me to run it in Ansys. The other thing that SpaceClaim does allow me to do, if I unhide this as well, is I have these. Well, I want to keep that hidden, the initial one. I can also export this as a step file, which I could open. So maybe I see this optimized design. I want to clean this up. Obviously, I'm not going to make a design that looks like that. I'm going to clean it up a little bit, right? So we can do that in SpaceClaim, but you may be more familiar with doing this in SolidWorks, right? So one thing you can do here is do a file, save as, and save it as a step file. And that's something you can open in SolidWorks. So if I choose a step file format, go to downloads, say new shape, and save. Now that's something I can open in SolidWorks, right? So if I wanted to go in SolidWorks and make a cleaner design out of this, that's one option to go from that SpaceClaim, that morphed, and this works in topology optimization as well. Take that morphed or topology optimization result, go into SpaceClaim, turn it into a solid just by right-clicking it. I think you have to do that step for it to work as a step file. Then you save as step file. Then you can open this in SolidWorks. If we got time at the end, I'll show you what that looks like. But so now we're done here. Once we've converted to a solid, this note though that it has the X across it or the slash, that does mean it's excluded from physics. So right now this won't show up in Ansys. So I do need to right-click that solid I just made and activate for physics. Okay, so right-click the solid. Make sure it doesn't have that slash on it. So right-click solid, activate for physics. Now I can safely close this window. We've got the geometry ready. So now what I'm going to do is double-click setup. Basically, we just need to rerun this now with the same boundary conditions. When I double-click setup, it does say I need to reread in some data. That was just exported from SpaceClaim. So I'll double-click that. So it's going to start the mechanical window again with this new geometry. So it may take a little bit. It's still loading, actually. What we see is kind of confusing at first. You see your initial geometry, which is not. We just have to wait a second. So So it flashes the initial geometry, then we'll eventually get the updated. The one thing with dealing with the faceted models, they are a little more complicated for Ansys to deal with, so they go a little slower. So one thing, you see this window where everything's transparent. What it's trying to do is saying, hey, you have a model. I don't know where the surfaces are for a bunch of selections. That's why our question marks are over here. And so this is trying to help us with those selections. That's why everything's transparent. I'm just going to close that. And so what we have to do is just go through with the question marks and reselect our selections. So one thing, the geometry doesn't have a material assigned. So we just need to click our geometry, and we'll switch that to structural steel. Okay, and again, we're just going to go through the question marks, do our modifications to get it to run again. The one thing that's different from what we saw before is we added that tetrahedron mesh. That's not going to work for us here. So we're just going to delete this patch conforming method. We're just going to delete it. And just kind of leave it with the default mesh settings for this model. So again, under mesh, delete that patch conforming entry that occurs under it. So we just have two more question marks. To fix support, we just reselect that left edge. Again, since the geometry change, it doesn't know we need to be in our context menu. Actually, it doesn't matter. We'll click that surface and do apply. Gets rid of the fixed surface question mark. We go to a forced question mark, which is going to be this surface here. That little dialog that's popping up is trying to help us select those. There may have been an option there to find the nearest surface or whatever, but these are just a couple, so it's easy enough to select them again. So once we have the fixed support selected on the left here, the force selected on the top, all our question marks are gone. We've assigned the material. We delete that option under mesh. So then we can hit solve, and that'll give us the total displacement, total stress. We can compare that to what we had before. Should run fairly, it might take a little longer to mesh than a normal model. It seems to be done meshing, and now it's solving. So as that's solving, I'm just going to look at where we were at before. So let's first look at our total deformation, because that's what we're trying to keep constant. Here we have 3 zeros. This is in meters. So it's 0.1138 millimeters. And if we look, it's now finished running. Look at our total deformation. It's a little bit higher now. We were trying to keep it constant. It did go up a little bit. We had pretty significant mass reduction, probably about 30-40% or so. We do have a little bit of increase in displacement. It goes from 0.13 to 0.17 millimeters. So it's not like, it's not perfect constraint. That's why I have to do this verification run. But it's pretty close with how much it morphed it and how much mass reduction we got. We can also look at the stress. So previously we had a peak stress of 81 megapascals happening at the base. Stress is a little tricky in these models just because it's really sensitive to the mesh. And we get stress concentrations at the boundary condition. But here we're getting quite a bit higher actually. But it could be a result of the mesh is a little, we have the stress concentration at the boundary condition, so it's not, may not be realistic there. But it looks like it's 410 megapascals. But we weren't really optimizing around stress. We were trying to keep stiffness the same. So that allows us to kind of check the results there. We can do a different optimization, and these are some options you can kind of experiment with on your own models. Like I said, these were the set optimizations that I found worked best on this particular problem. And that was, again, the mass minimization and a constraint on the compliance. The default was maximize compliance instead of mass target. That's more good for topology optimization than it is for morphing. But the one thing you could do is do mass minimization and a response constraint on stress. So then I would delete this response constraint, and I could insert, again, I need to be in the context menu, insert a stress, global stress, I believe. There we go. And I could set a max stress. Though stress is, like I said, it's a little tricky in these problems because you get that stress concentration at the boundary condition that technically is an infinite stress concentration. So it really gets to depend on mesh size. On this model, I didn't find that the stress approach worked very well. One thing that could help there, and I didn't try, is you could do a local stress, and I'm not even sure how that one works, but it may allow you to narrow it in on a particular surface or something that may work better. So you can experiment with different things. I did find that the compliance target works best on this particular model, but there's other options to try.